Well, my presentation talk will be on keeping people alive and healthy in space based on some of the work that's ongoing here at the University of Colorado. And yes, I am Associate Professor James Nabity. Just a little bit of background about me. From Central Nebraska originally. I got a master's degree on fellowship while I worked at the Naval Air Warfare Center. It's now a Naval Air Warfare Station. They've changed their names a number of times. And at that point, I was working on propulsion, but it got me involved with chemically reacting systems, which ultimately got me back to my love for human spaceflight, which I became involved with when I went to industry for several years, working in small business. And then I've been at the University of Colorado for about the last 8+ years. We have a number of research thrusts at CU Boulder with focus on spacecraft and habitat design, astronaut health, and this is really part of my effort in terms of keeping the crew alive, and space life sciences. And all of these basically flow into the field of bioastronautics, which is the study and support of life in space. So what are some of the challenges associated with long-duration human spaceflight? Well, one is habitat design, actually building a spacecraft or a habitat that can make provision for all of the needs of the crew. And there are a number of ways to do that. One is leveraging in situ resources. I use, and my students utilize, some of the simulants in order to explore the feasibility for extracting metals or oxygen from regolith, using that as a soil media or a soil substrate for the growth of plants. We look at, in particular, regenerable environmental control and life support systems, as it's called. And we're concerned with protection from the radiation environment and how to sustain crew members when they're on EVAs, extravehicular activities. So I have a number of students, both past and present, who are working some of these areas. And if you look at this, you'll see a diverse set of research activities that are either ongoing or have been happening. And one of our current focuses is really on the robustness of technologies. As most of us are probably aware, most of you are probably aware, International Space Station has certainly been a proving ground for environmental control life support. And there have been a number of challenges that have been faced, particularly with CO2 removal and with water treatment, water recovery and treatment on board space station. So when we think about, the hazards of space to life and health, vacuum obviously is one of those problems. And if we think about other atmospheres, for example, the Mars atmosphere, which has roughly 95% carbon dioxide, 1% carbon monoxide, a little bit of nitrogen and oxygen, argon. But these environments are hazardous to people living in these environments. Temperature extremes. The lunar surface, for example, from minus 250 Fahrenheit to plus 250 Fahrenheit. The damage or challenge with micrometeoroids. In low Earth orbit, we're additionally faced with the other objects that are in low Earth orbit that pose a crew. So orbital debris, weightlessness, and gravity fields. And of course, if we talk about transit to either lunar or Mars environments, there is a period of weightlessness before transitioning to these reduced gravity environments. And then, of course, space radiation. So what is the importance overall for ECLS to support habitability of people in space? Well, when we think about it in terms of a timeline, and I illustrate this from left to right in terms of the influence from seconds to months to years as we go across. And I start with the loss of a breathable atmosphere because that is the thing that would potentially cause loss of life in space immediately. And just to give some influence, loss of a breathable atmosphere can result in loss of consciousness in seconds, loss of life in minutes. And this comes from a wonderful resource called the Bioastronautics Data Book. And then as we go down that list, there's the influence of toxic gases such as metabolic carbon dioxide. If an individual were enclosed in a room and naturally breathing and respiring The respiration of CO2 will build up to the point where it could cause a toxic environment before loss of oxygen. And so it's just something to be aware of. Extreme temperatures again. And it just depends on the environment as to how quickly that will potentially be a problem. Lack of water and food. We're all aware of scenarios where people have been able to survive without water for 3 to 7 days, food 8+ days, depending on the conditions that they're in. But these two are problems. And other hazards, such as radiation, the risk of injury and treatment. Fire on board space stations or space habitats is particularly problematic because of the influence that it'll have on the surrounding atmosphere because of smoke and contaminants that are produced, the toxic gases. And we're in this confined space, so it's not like we can just open the window and escape. So this leads to a number of design drivers when thinking about environmental control life support systems, and they depend on the mission objectives. NASA has been focused on a number of these. When we think about commercial space flight, this environment particularly could expand even more. When we think about in the last year, we've had the youngest crew member go into space, the oldest crew member go into space to date. And that's occurred on commercial vehicles. So destination matters, the diversity that's associated with the makeup of the crew, those humans that are going into space, whether they be tourists or professionals. And ultimately that influences things like the space habitat design, the level of robustness for the technology that has to be implemented, human factors considerations. Because associated with this diversity in the range of humans that are being now flown into space, they may have special considerations that are required for either physiological health or psychological health. So meeting these challenges really entails, first, we want to keep the crew alive. We want to keep these people alive as they go into this new environment, the space environment. And preferably keep them healthy, happy, and productive, which translates ultimately to robust vehicle and life support system design, as well as some biomedical countermeasures for human factors and a number of operational concepts. And when we think about commercial vehicles, bringing these perhaps paying customers into the environment of space, the risk that's associated with this activity is something that must be conveyed as well. So when we think about the human subsystem and what that might mean, I've outlined it here in terms of inputs and outputs. Some of the key metabolic outputs for the crew would be oxygen, water, and food. And then I illustrate nitrogen in terms of maintaining a comfortable pressure. You know, we think about our atmosphere pressure, it's mostly sea level static, perhaps to some range of altitude. And the question for our spacecraft designers for space habitats for people is what environment to establish. And of course, that depends partly on the mission, what activities are being planned. The outputs are simplified here, but carbon dioxide is certainly one of the common ones that's important to consider, and we must remove. Respired and perspired water, we want to recover that and treat it for potable water. The same with urine, recovering the water from that, and then treating the brine for storage. Perspired solids, feces, and then ultimately, of course, metabolic heat. Most space habitats are designed to be essentially like thermos bottles, where the crew member is, and along with other equipment, heat-producing equipment, is enclosed in this insulated environment. And so that heat has to be eliminated in order to prevent overheat of the crew members. And then when we look at some of these requirements in a little more detail, and what I encourage is just focus on the oxygen, the very top one, in terms of a reference crew member needs approximately 0.8 kilograms of oxygen per day. And the respired output from that in terms of carbon dioxide is about 1 kilogram per crew member per day on average. Well, again, when we talk about the range of human physiologies that might be transported into space. And just to illustrate it, this is a 5th percentile female, has on the order of a need of about 0.6 kilograms, produces roughly 0.8 kilograms of CO2 per day. And if we look at the 95th percentile male, needing on the order of 1 kilogram per day of oxygen, producing almost 1.3 kilograms per day of CO2. And this is NASA's type of numbers. When we think about commercial vehicles, the range of parameters that a life support system might have to treat goes even beyond these limits. We're talking greater deltas. And so there are some significant challenges that are posed ultimately in terms of the environmental control life support system for space. So what are some of the key functions that must be provided? Well, we've already seen atmosphere, water, and food. But in addition to that, there's this need for waste management, particularly for crew safety, which includes the fire detection and safety, but also radiation protection, medical facilities in order to treat not only injuries, but just conditions that might arise in human spaceflight. But atmosphere is key, and that's why you see this long list of parameters that are necessary in order to maintain a breathable atmosphere in the space environment. Not only provide oxygen and remove carbon dioxide, but we almost also filter out particulates and microorganisms. Remove volatile organics that are, again, toxic contaminants that could impair the crew. Monitor and control the partial pressures of all these. So the composition, overall makeup of the gas, and maintain that total cabin pressure. Keep the temperature and humidity at a very comfortable level. So roughly 70 degrees Fahrenheit, 40% relative humidity for the comfort of the crew. Think of shirt sleeve environment is what we're trying to maintain. And then because in a microgravity environment, there's no natural convection available to distribute or help maintain a breathable atmosphere throughout the cabin. It must be some forced convection. So fans are required in order to do that, particularly between modules. So some of the considerations for human factors associated with environmental control life support, physiological factors, as you've just seen from the prior diagrams. Sex, weight, and age can all influence those. Then there are other factors that can be important in terms of how exciting is the event, and that things like vibration, lighting, noise, and ecosystems, particularly these fans that are required to treat and revitalize that atmosphere, they tend to be noisy. So that influences then how we deal with crew accommodations, ergonomics, and ultimately what that might lead to in terms of crew behavior and interactions during the environment that they're part of. And then, do we need exercise facilities? Do we need to support other crew activities, social activities that might be required? So this is all influencing habitat design, which ultimately then influences the need for ECLS. So I just want to wrap up with this diagram, and this is an illustration, a schematic of how it's done on the International Space Station. But I show this to really illustrate the complexity and the interactions that are associated with an environmental control life support system. So if we look at this, we have the crew in the center. And let's just kind of start top and move around, circling to the right. So we have this temperature and humidity control that's influencing or part of the atmosphere revitalization system, this quadrant to the right, where we have air provision for CO2 removal, trace contaminant removal that removes those volatile organics that I just talked about, also removes particulates. One of the things that's been investigated to reduce the need for consumables, so resupply from Earth back to space station, is a Sabatier system, which chemically reacts the carbon dioxide with hydrogen to produce methane and recover oxygen in the form of water. That water can go to a water processing plant, which basically can then be treated for either producing potable water, drinking water for the crew, or via electrolysis produce oxygen. Obviously, waste management. On board space station, solids are basically packaged into what are called these footballs. Essentially, the trash is packed in a garbage bag, Ziploc type bag, that's sealed and then duct taped in order to store it until it can be returned to Earth or burned up with a Progress vehicle. Feces are stored separately, and they are chemically treated and siphoned. Urine, as I've mentioned, water is recovered from, and the brine is stored separately, again, treated to siphon it from biological contamination. So there's a fairly complex, integrated, and highly interactive system with the crew at the center. And then most of my research has been focused on this area of atmospheric revitalization, given the challenge that it poses for keeping the crew alive.